Chemistry with Pastor Dan. We're talking about new concept solutions, and here we're only going to deal with key terms, so there won't be any math at this point. There will be eventually coming, but we're going to look at solutions. Now, we talked about solutions way at the beginning of the year. We talked about matter. We said there was two parts. Remember, homogeneous looks the same all the way throughout. Heterogeneous, distinctive differences. We said homogeneous was either going to be an element, a compound, or a solution. Now, when we talked about solutions there, we said that they were defined as homogeneous mixtures. Now, again, as I said, homogeneous means substance uniform throughout. They look the same all the way through. Over here I have water. Water is a compound. It looks the same all the way through. But it's not directly because it's also a mixture, which means two or more substances combined physically. We put them together, we can put them apart pretty easily, and that's how it works. Now, when we look at them, look at solutions, there are specific parts to it. There are two parts. The first is called a solute. Now, a solute is defined as a substance to dissolve. All right, over here, I have my water, and over here, I have some salt. Salt in salt water is my solute. My water is my solvent. Now, solvent is defined as substance doing the dissolving. So water here is dissolving the salt and separating it into its parts, a process we call dissociation. All right, now, there are specific types of solids. Now let's take a little bit, just a titch. Whoa, it's a little more I wanted to do, but we'll see what we can do. I'm going to take a little stirring rod, stir my salt up. Hopefully I didn't put too much in there. I might have. Get it all to dissolve up. Okay, there we go. It's going pretty good. Okay. Now, as you look at that, the salt itself is dissolved. It looks all the way through, all the same. Pretty high concentration. But if I had just put a little bit less, we would say that it's unsaturated. That means that there's less solute in there. There's more room in here. I could still put more in. Now, this is pretty close. You can see the color is pretty cloudy because it's pretty close. This is close to what we call saturated, which means it has all that it can hang, can't take anymore. It's all the way filled up. So when it's reaching its max capacity that the solvent can hold, we call that saturated. And the last one, unsaturated, less saturated, all, then it's not a bird, not a plane, but super saturated. Super saturated is defined as having more. How can you get more? Well, if I heat this, I increase the temperature of the solution, which gives more movement inside of there. And as a result, more collisions take place, so I can dissolve more in. And if I cool it down really slowly, I can reach a supersaturated state. Let's put these back over here. All right, get them out of the way. Now, next thing we have is there's four additional terms we call miscible, aqueous, tincture, and alloy. Well, what do each of those mean? Miscible means two liquids. If I take alcohol and water, pour them in, they dissolve equally into each other. When two liquids can dissolve into each other, we call that miscible. Okay? Next, we have an aqueous. So over here, that salt water, we would consider that aqueous. That's an aqueous solution. All right. Next, we have that tincture. Now, if the solvent is not water, but alcohol, that's a tincture. And the last one we have, I think you probably have one in your pocket. I do too. Alloy, like a coin, just dropped one on the floor there. That is a metal solution. Okay, we can separate them out. We can heat them up and get them separated into the individual parts. All right, now, last thing we're talking about here is the concept of solubility. This is measure how much solute will dissolve. I already showed you the water, and I told you different things that we can do to increase solubility. First thing we can do is we could increase temperature. Now, that does not work for all phases, and I'll show you in a second. Two of the phases go one way, and one of the phases goes the opposite way. but temperature can affect solubility. The second one is stirring, and I showed you that with my salt water here. Remember, I stirred it, and the reason why that is I stir it, I get more collisions between my solute and my solvent and causes them to dissolve more rapidly, and that's another factor that can increase solubility. Third factor is particle size. Think about a sugar cube. If you get a sugar cube and try to dissolve it, it takes quite a bit of time because they're all packed together, not a lot of surface. Now, if you take granulated sugar, where the particle size is smaller, it dissolves faster because there's more area to interact. And the last one is gas, but gas only increases solubility with increased pressure for gases only. It has no effect at all with solids or liquids because, again, that would go back to Boyle's law we talked about before. So if we're increasing pressure, we're decreasing the volume of the gas, make the gas smaller so it can dissolve more rapidly and easy. That's how they get the carbon dioxide inside of your pop, so that when you open it up, the pressure comes off and the bubbles start coming out. That's how that all works. Now, this is a graph that talks about when I mentioned before about temperature and solubility. For solids and liquids, okay, as we increase temperature, we increase solubility. I can get more solid and liquid dissolved at increased temperature. But gases work the opposite. Why? Because as you're increasing the temperature of a solution with a gas in it, also you're getting the gas to move faster and it gets more energy and it can escape out. So as a result, it's the opposite process for temperature. It works in that way. Now, there is one last rule we'll talk about, and that rule says likes dissolve likes. What are we talking about in likes dissolve likes? We're saying that polar solids are dissolved by polar solvents. Now remember, we talked about polar earlier. Water is polar. I have to have hydrogen and at least one unbound electron pair to be polar. So water is polar. Salt then would also have to be polar because salt dissolved into that solution. Now I got to be careful with the next one because that also means nonpolar substance dissolve nonpolar solutes. Okay, over here, be very careful with this. I have styrofoam, and I'm sure you've put water in styrofoam before. Nothing happens because styrofoam is nonpolar, water polar. Nothing happens. Over here, I have a solution called methyl ethyl ketone. I want to be careful not to get too close to the computer. Computer has a lot of plastic parts, and you can see almost immediately it begins to dissolve, and my styrofoam. Now I got to be careful because ketones aren't very good for you, and I don't really want to get that on my hands. All right, so I'm going to push down with this, but you can see that it dissolves up completely, and my styrofoam cup that I had here all dissolved. All right, now I'm going to show you next time a little disc what happened from this particle as it got dissolved. All righty. Now, there's one more thing I want to talk about here, and that's the concept that water is known as a universal solvent. Now, does that mean it dissolves everything? No. That only means that it dissolves substances that are like it, and a lot of substances are polar, so therefore that's what we call the universal solvent. Hopefully that wasn't too bad. Take care, be good.